All right, welcome back to the next podcast of our beginning of Unit D. And chemical equilibrium hopefully is feeling okay to you guys, including those ice tables with our initial, our change, and our equilibrium concentrations. We're now going to go into something called equilibrium laws. Now, the equilibrium law is a pretty snazzy way that you can take the concentrations of the various reactants and products at equilibrium and recognize that they always end up forming a consistent constant, which is pretty cool. And this allows us, knowing the concentrations of the others, to predict an unknown. It's definitely algebraically geared, and it's a super, super useful way to get extra information when some isn't recognized. So I'll show you what I mean. An equilibrium law, by definition, like I said, is algebra, right? Which means there's an unknown where you can figure out that unknown as long as you have all the other variables. And these laws are based on perfectly balanced, keyword here, equilibrium reactions. So the concentrations have to be specific to when the reaction is at equilibrium, when the forwards reaction and the reverse reaction are happening at the exact same rate at a constant temperature. Now, here's the deal. If you look at this, this is your general equilibrium system. And I can see when this thing reformatted to a PDF, it did something weird. So I want you to imagine, I'm going to outline them in red, those equilibrium arrows, shift them over to the left. You can see this on the real notes. There should be a little C in front of the great big C. Okay, so it should look more like that. It's just that it got cut off when it changed to, as I said, the PDF. Anyway, if this is your general equilibrium system, now guys, you can visualize this. What if there were 3 products? Then we would have to add another one plus lowercase e, capital E. Or what if there were 3 reactants? Same idea. You would have A, B, and C reacting to form D, or to form D and E and F, or whatever. You can vary it as needed. But ultimately, the way this equilibrium law is formed is it's always going to be that Kc, which is representative of the equilibrium constant, okay, is equal to the concentration, and this is important, the products on top, that's going to be your numerator, always, divided by the concentrations of the reactants, which is your denominator. Notice the square brackets representative of concentration. And in terms of what the whole thing as a law is built up of, I'm going to go through and do a little bit of highlighting to show you how this works. Now we've got A lowercase, B lowercase c, and lowercase d. These are all the coefficients, hence the balancing. And you can see down in the equilibrium law, those exact same coefficients are being used as exponents on the concentrations. This is key. Now, in terms of what is that CDAB in the square brackets, those are representative of the concentrations of each different chemical. So in other words, we're taking the concentrations of the products, raising them to the exponent of their coefficient, and multiplying them together. Then we're dividing that whole amount by the concentrations of the reactants, raised to the exponent of their coefficients, and multiplied together. Be aware, when you're doing this mathematically, the entire top brackets has to be divided by the entire bottom brackets, right? So the exponents are coefficients, and the uppercase letters and square brackets are molar concentrations. Now, key thing though, those are your molar concentrations at equilibrium, right? It's not the change in concentration. It's not the initial concentration. It's the equilibrium concentration. That's really, really key to recognize. And I mentioned it, but I'll write it down for you. That Kc is representative of the equilibrium constant. Now, essentially what will happen is every reaction will have an equilibrium constant associated with it. And it is a consistent equilibrium constant, provided that the system has allowed to be reached equilibrium at the same constant temperature and pressure. Okay. Let's go into this. This first lesson here is just going to be about properly building these equilibrium laws. We're not going to do any calculations yet. We'll get to that in the next podcast. But there are a few rules associated with this. And if you got the rules off, you're going to make the laws wrong. So rule number 1 is no exception. If you've got a gas, you have to include it in the equilibrium law. Okay? And yeah, these are a little bit of memorization. It is what it is. That means when you're asked to write the equilibrium law, this will happen in a question. So it's like, boom, here's your equilibrium reaction. It's balanced. Please write the equilibrium law. You would write down and be like, okay, got it. Kc, because that's my equilibrium constant, equals. Now we're going to do the concentration of the product first. So I'd square bracket it. SO3, write the state of matter, gas, square off the bracket. I have a coefficient of 2, so I make that raised to the 2, exponent 2. I put that whole thing over. My reactants are both gases, so they get included. I'm going to have SO2 gas, once again squared because of the coefficient. Right beside it, because they're multiplied, concentration of O2 gas. The coefficient is 1, and we don't have to write the 1. It's assumed. Dun, da, da, da. That is your equilibrium law for this particular reaction. You don't have to put these brackets on the bottom. I'm going to, just to remind you, it is that whole top divided by the entire bottom. From a calculator perspective, please be careful about that. It's a silly mistake to get a question wrong for. So all gases are included. Here's your next one. Aqueous ions and aqueous molecules. So for example, if you have any sort of an acid dissolved in water, if you have any sort of say sucrose, glucose, there's many examples, dissolved in water. If you have sodium chloride that dissociates into sodium ion, chloride ion, all of these are aqueous ions or molecules. They will always be included. Make sure they are a part of it. So if you look at the example given below, every single one of these are aqueous. So every single one of them will be a part of the law. Once again, we say Kc is equal to. Common mistake is people put reactants on top instead of products. Pay attention to it. Make sure that that's something that you're watching. It'll be the concentration of the NH4 plus. Make sure you're putting states and the proper charges times the concentration of the CH3 COO negative, that acetate ion, square bracket, all over. And then we have a molecular compound, ammonium, which is, that ammonia is aqueous. So it's included. Whoopsies. I want those to be square brackets, not rounded ones. Multiply, not times, multiplied by our CH3COOH. Again, it's going to be aqueous. There we go. Done and done. Again, the entire top is divided by the entire bottom. Okay, so where we got so far? Gases are always included in the law. Aqueous ions and molecules are always included in the law. Let's go to the third one. In this one, pure solids are never included. Leave them out. So literally, if you examine this and we see gold ion, yes, that'll be included. We see fluorine ion, yep, fluoride will be included. And then we see gold fluoride solid. Nope, literally, leave it out, not a part of it. Like I said, few rules to memorize, guys. Okay, we end up with then Kc equal to, if there is no concentration to put for the products, I put a 1. Okay, we still have to have an entity there. It's not 0. Then on the bottom, we're going to have Au3 plus aqueous, square brackets, times F negative aqueous to the exponent 3. And there you have it. I know that the 1 might be confusing. Here's the deal. These equilibrium laws are a little more complicated than how they're being presented right now. We start with them being very, very simple in regards to Chemistry 30. Technically, there are other ratios involved here related to what's called activity. So in actuality, every single one of these is a ratio over a ratio, which means we end up having a non-activity or non-activity, which equals 1. So yeah, kind of a side explanation, But be aware the 1 is logical because there is an entity over itself, which will give us the 1. Okay, let's keep going. To summarize so far, include all gases, include anything aqueous, leave out pure solids. Okay, what's a pure solid? It's a pure substance, which is a pure element or a pure compound in solid form. To continue, here's our 4th one. Pure liquids are also never included. Okay, so analysis-wise, HCN aqueous, that gets included, it's aqueous. H2O liquid, ding, 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 a pure substance that's a liquid, leave it out. Hydronium aqueous, leave it in. Cyanide ion aqueous, leave it in. So implications of this, the equilibrium constant is going to be equal to the concentration of hydronium aqueous times the concentration of a cyanide ion aqueous. It's balanced with 1, so we're good to go that way. All of that over the concentration of the hydrogen cyanide, HCN, hydrocyanic acid, aqueous. There we go. Done. Do not include the water. So that, folks, is your basic rules for equilibrium laws. Now, putting that into practice then, well, ultimately it's just a matter of looking at the reaction and going, okay, what can I include? What should I leave out? So go through it step by step. Iron 3 plus aqueous. Yeah, you bet. It's aqueous. Solid silver. Any solid left out. Here, I'll make a bigger X so it's obvious. Okay, iron 2 plus ions. Oh, for sure. Silver ion. Absolutely. So we have only one of those entities from a concentration perspective that is left out. So when you write the equilibrium law, we would say Kc is equal to the concentration of the iron 2 plus ion times the concentration of the silver plus ion, all divided by, again, leave out the silver solid, the concentration of the iron 3 plus ion. Yes, it is that simple. Hopefully you can start to see where we're going with this in the next lesson, where we're going to plug numbers in for these, right? But you got to get the laws right first. Check out the next example. Okay, at a glance, what can you leave out? Well, definitely not the gas. It's got to be there. So gas is a go. Solid, pure substances. Oh, it leaves both of these. They're gonzo. How does this actually look then? Similar thing. Kc, equilibrium constant, is equal to the concentration of the carbon dioxide gas, needs to be there. Okay, the exponent's 1, fine. I'm going to put divided by 1. You wouldn't have to put that there, guys, but technically ratios will cancel out. It's always over 1 anyway. I mean, honestly, you take the number 4. 4 technically is 4 over 1, right? There it is. Equilibrium constant. Check out the last one. Same process. Aqueous is a part of it. Aqueous is a part of it. Liquid, no. Solid pure substance, no. Gone and gone. Therefore, my products, 1, I don't include either of them. Concentration of the HCl, aqueous, coefficient 1, so exponent is 1. Concentration of the titanium 1 hydroxide goes next. Aqueous, coefficient 1, exponent 1. There you have it. There's a couple questions you can do with this that are specific to just writing accurate equilibrium laws. So you can get a bit of practice with this. Remember, leaving out pure substances that are solids and liquids, and always including gases. Pure substances or not, include your gases. And always include your aqueous ions and molecules. So please do all of number 3. There's a few equilibrium laws that you can do for that one. And in the next podcast, we'll start doing some number crunching with those. Talk to you soon.